Okay, let's start then. If you can write the title down. Single and two support, principle of moments. Okay, it's lemons. You don't like the smell of cleanness?
There is a smell.
Whatever cleaning product they use, it's lemon scented. You don't like lemons? You can open the window if you like, it's no problem.
I'm just curious about the different smell.
Okay. Why, what do cleaning products smell like for you back home? No? Lemon? Lemongrass. Is that like lemons?
No.
Okay.
It's a bit different.
Okay, alright. Okay, did you write that down, principle of moments?
Yeah.
Okay, so, have a look at this picture here. What would happen if equal but opposite forces are applied at the ends? So, let's imagine here is our piece of wood, and we have a force here, and a force here. What will happen?
Nothing.
It seems like nothing, doesn't it? Because the F equals the F. So it seems like that should cancel that and nothing happens. Not true though. Yeah, what will happen is it will start to turn. Yeah, now this is quite interesting because at first you might say, well, this is an up, this is a down, they're equal, they cancel, so nothing happens. But we need another perspective. Not only do we have an X and a Y to think about, you know, right, left, up, down, we also need to think about the direction this way, and then the direction this way. What do we call these directions? Does anyone know? So we have, this one's called horizontal. You know this word horizontal? Yeah, and what's this one called? Vertical. But what is this direction called? Very good. Anti-clockwise. And so, of course, this one running the other way, that one's called clockwise. So in this example here, if I take this as the turning point, is this clockwise or anti-clockwise? This guy? Anti, so I'll write an A here. And this guy? No, anti. It's going this way around, isn't it? So you have two anti-clockwise forces. So then it will rotate anti-clockwise. Now watch what happens if I remove this and put it here. This is anti-clockwise, and what's this one here? Clockwise. So maybe it's possible that these cancel, although they don't in this picture. Why do these forces not cancel? True, one is up and one is down, and one is anti-clockwise and one is clockwise, but they don't actually cancel. In this picture, it will move anti-clockwise. Does anybody know why? The distance is important. Yeah, this distance is smaller than this distance, which means the turning force here, that will be bigger than the turning force provided by this one. Because remember, we said when turning, it's not the force we care about, but the force and the distance. Okay, so anyway, you don't really need to write this down if you don't want to, because everybody knew these words, and I think you get the idea. Yeah. So we have a look at this. It would seem the wooden plank should not move, but it does. So what gives? While the plank is moving, it's rotating. So a turning force is making it turn. If it's not turning, then we say it's in equilibrium. Okay, so this word equilibrium means it's not moving up, it's not moving down, not moving left, not move. No, that's not true. Let me say that again. Equilibrium means it's not accelerating up, it's not accelerating down, it's not accelerating left, and it's not accelerating right, and it's not rotating. Everything is balanced. That's what the word equilibrium means. Now, that's an important word, so I do want you to write that down at least, equilibrium. Did your brother study computer science in high school? No. So it would be fair to say that you're smarter than him. Would that be fair to say? Perhaps, yes. Yeah, go on, say yes, yeah. Don't worry, I won't tell him he said it.
I studied more, but maybe he's smarter.
No, clearly you don't know your brother. Clearly. Do you get to visit him much, or not so much?
No, after you want to go,
yeah. Okay, did you write that down?
1 minute.
Yeah, sure. Now, you don't have to write these exact words down. I just want you to write down some meaning of equilibrium. So, you could even just say, equilibrium means that everything is balanced in the forces. The left, the right, the up, down, the clockwise, the anti-clockwise is all balanced. Yeah. Okay. Oh, I actually have a precise definition, I forgot. An object is in equilibrium if the total net force is 0. Yeah, well, that's a shorter way of saying it. Although I should really say the total net force and turning force, if you want to be extra clear. So, what does that mean? That means, therefore, the force to the left equals the force to the right, obviously. The force up should equal the force down. And what's the last equation I could make? What do you think is the last one? Yeah, you think you know? Go on.
Clockwise.
Yeah. And turning force clockwise equals turning force anti-clockwise. Yeah. So all the forces are balanced here. Okay. Can I continue? You're writing this down? Yeah. Continue? Okay. The last point is in fact known as the principle of moments. Or maybe you could even say conservation of moments. The idea that the clockwise and the anti-clockwise are equal then. Yeah. Can I continue? Yeah. So, that is the sum of the clockwise moments is equal to the sum of the anti-clockwise moments. Okay, so I think it'd be good now to have a look at an example of this new formula. A 40 kilogram boy sits at the end of a 100 kilogram seesaw, and his sister of 30 kilograms sits at the other end. Okay, so let's draw this. Okay, so the boy and the sister, 40 kg, 30 kg, and the seesaw is 100. This is 100 kg. So that means this force here, what's the weight here? What's the weight here? How would you get it? Oh, you don't have to work it out. Tell me how you would get it. What is it? It's mg, yeah, so it would be 40g. And this one would be 100g, 100 times 9.81. And this one is 30 times 9.81. Okay, the pivot is in the center, so we know that this is 2.5 meters, and this is 2.5 meters. Their father decides to fix this by moving the pivot from the center to the new location. Where must he put it? In other words, the father wants to know where should he put the pivot so that the seesaw is balanced. Because if he puts it in the middle, what would happen? It would rotate anti-clockwise because the boy is heavier on this end. So we need to put this somewhere in the picture. We don't know where. Let me just draw it here for the moment. And we're trying to work out the x from the end to the middle here. Okay. So let's have a look here. How many forces are acting on the seesaw? How many forces are on the seesaw right now? How many?
3.
Not 2 and not 3. There's one force I didn't draw. What force did I not draw? Yeah. There is one more force here. Okay. Now, if this is in equilibrium, we know the forces to the left should equal to the forces to the right, but that is useless because there is no force left and right. Okay. The next one is the forces up should equal the forces down. That is useful because I can say or should equal 170 G, which I'll calculate actually. Whoa, that's that. 1667.7. And lastly, I can say the anti-clockwise and the clockwise turning forces must be equal. So let's begin. Let's start with this one. Is this clockwise or anti-clockwise? And this is the turning point. This one is an anti. This one here. Clockwise, this one here. Clockwise, and this one here. This or. Not clockwise. Not. Oh. Is it clockwise or anti-clockwise? No, tell me why you're confused. Maybe I'm trying to trick you. It's neither. Why not? Why is this nothing? It's on the turning point. So if the force moves through the turning point, it has no effect on turning. So only the boy and the girl in this picture and the weight of the seesaw can cause it to turn. The reaction force at the pivot, the fulcrum, the reaction force at the fulcrum does nothing to rotate it. The only thing the reaction force is doing is cancelling these three. It's, as someone was saying, it's an up force. It has no effect on rotating it. Okay? So, we need this to equal this plus this. Alright, so let's do the first one. That's 40G, and what's the distance here to the turning point? The distance here to the turning point, what's that? Not quite. Because the turning point is here. It's an X. Sorry, that's not clear. That distance to the pivot is X. Okay, the next one. So that should equal this force. Now, to be very careful, what's this distance here? Who can see what this distance is?
2.5
Very good. 2.5 minus X. Plus the girl, 30G times. Now, what's the distance from the turning point to the girl in this picture? 2.5, not quite. That's 2.5, so you're right there, but you need to plus this distance, not the X, that's the other distance here. Yeah, but if we just say how you were saying it there, it's 2.5 plus 2.5 minus X. Because we just said a moment ago that distance there is 2.5 minus X. So from here to the girl will be that plus another 2.5, which of course is 5. Alright, so that's 100g times 2.5 minus x plus 30g times 5 minus x, and that's 40gx. Now, what can I cancel here nicely? What can I cancel from everything? G can nicely cancel, can't it? Off it goes. So 40x equals 25 minus 100x plus 150 minus 30x. I hope I did that right. So that's 170 x equals 100 and...
Why is this the 75?
Is it not 25? Oh, of course not, thank you. It's 250. Thank you. Is everything else okay?
Yeah.
Yeah. So that's right. 400? Yeah?
Yeah.
So that means x is 400 over 170. .35 meters is the answer. So he needs to move it 15 centimeters left. If you want to think about it like that. It first started off like this, and he had to move it 15 centimeters to the left, so it could be here. Yeah, is that okay? I don't know how hard you find this. You might have even done something like this before. Is this okay for you, this example? Or it's not okay? You're unhappy?
Yeah.
Tell me what your question is, if you have a question.
That.
Hang on, let me number these. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, which one?
From
From 2 to
9.
3, or 9.
No. Yeah. 3 to 3.
2 to 3.
Yeah.
Yeah, I suppose these are separate. This is like A, B, C. And what I did was I used these three.
Mm-hmm.
So A, I said, was no good, because here there is no left and right. There's only up
Up and
and down. So this one, no good. The next one, up equals down, is this one equals this plus this plus this. That's that. The one going up should equal that, that, and that. And the last one, this one. Do you know the meaning of this word? Clockwise? Yeah. And this word you know?
Yeah.
Anti-clockwise. Okay. So, if you look at the picture, let me draw it again over here. This is the center. This force here wants to make it turn anti. Yeah. And then the two forces here want to make it turn clockwise. Yeah. So the turning force here should equal this one plus this one. And what is turning force? We did that in the last class. The turning force is F multiplied D. So the distance is the distance from here to here, here to here, and here to here. They're the three distances. That's how I made this. And this is really the key. This is the key one. In fact, did I need this? No. Did I even need this one? No, I didn't even need this one. It was this one that I needed. So this was the important one. I don't know. Does that help you?
Okay. Then.
Oh, yeah.
A.
Yeah.
R. C. C. A. That means R is turning point U.
Yeah.
And.
Or is the turning point, yeah.
Then the C is the pointer.
The C?
No, rep C.
Oh, this C?
Yeah.
Oh, my picture's terrible. Yeah, sorry. There's a small distance here. This is the turning point.
Yeah.
You're right. This is the turning point, and this is a force going down. And there's a small distance here of 2.5 minus x. Isn't that what we said? For this distance.
Okay.
It's okay? Okay, great. Any other questions? Is okay over there? Yeah. And down here, is okay? Alright. So let's look at another example now, make it a bit harder. Or do you need a minute to write this? Yeah? Okay. Maybe you should buy a notebook, or are you happy doing this?
Yeah, I like it.
You like it? Okay, but where do you put it at the end of the day when you're finished? Do you have a, oh good, okay, fine. And are the pages numbered?
Yeah, I am.
You have a number? Wonderful. Okay, in a moment we'll do another example. Can I continue? Yep. Alright, so a 100-gram meter stick is suspended by 2 strings. Okay, I hope you all know what a meter stick is. It's a stick, and guess how long it is? Yeah, so funny. A meter. So we start here at 0 centimeters, and this is 100 centimeters, and it's 0.1 kg. And I'm hanging this from 2 strings. The first string is at 25 centimeter mark. So there's a string here. Well, I should draw a bit more, maybe here. And this is at 25 centimeters. And then there's another one at the 90. And that is it. And of course, the weight is at the 50. This number here on it is 25, this number here on it is 50, and this number here on it is 90. Okay, and this force we don't know. Let me call it T. This force we don't know. Let me call it S. And this force we do know is 0.1 G. Yeah, which is 0.981 newtons. Right, now this question is a little bit different because now we have 2 things to find. Firstly, is there any left and right force? No, so let's look at up and down. So if I look at up and down, what equation can I make? What's the up force here? What force is acting up? What's the total? Go on, don't be shy. Thank you. And that should equal? 981. Okay, good. Now I need to make a second equation. I can use the turning force. Now, here's the big question. Take a minute to think about this. Where is the turning point? Right, what do we think? Any answers? Let's see, where do we think the turning point is? Go on, what are you saying, yeah?
I don't know, why would there be a turning point?
Well, there has to be a turning point if we're talking about rotating clockwise and anti-clockwise. For example, in the last example, you could say the same thing. Why should there be a turning point here? Is it seesaw? Yeah, but you're right. But suppose suppose I take an extreme example, okay? Here's a meter stick, right? And I hang it here, and that's it. Will it turn? Of course, yeah. So where's the turning point in this picture?
No.
I think we all would be happy to say it's here. Now, what about if I do this? We'd be happy to say it's here. Yeah. What about if I put it on my finger? It would be here. Okay. So, where's the turning point in this picture?
But then there's two string, how it turns.
It doesn't, because the turning forces cancel. They cancel, so they don't turn. But the question is, where does the cancelling happen? So it's not turning around what point? It's not turning. It's not turning around what turning point? You're saying S, okay? Where else could it be? We have one answer. Could be S. Where else? Anyone else?
Between 50 centimeters and 100.
Oh, I see. So you're going to say somewhere like here. Okay, excuse me. Like here. Okay.
Bit more to the
Oh, okay. Here?
bit more.
Here?
More?
More.
Here?
Yeah.
Okay. Any other answers?
25 at middle of 25 to 90 cm.
The middle of 25 and...
90 cm mark.
Oh, what's that, like here? Alright, okay. Any other answers? Nobody wants to say T. No, okay. No. And nobody wants to say the middle.
They're at teach.
No? Okay, so I'll give you the answer now. So the correct answer is... all of these are right. Yeah. What I didn't tell you in the last example is, believe it or not, you will get the same answer no matter where you draw the turning point. Now, a lot of students get very confused by this and don't believe me. So I promise you, if you put the turning point here and use this to calculate T and S, or even if you put the turning point here and use this to calculate T and S, you'll get the same answer. Now, sometimes students don't believe me and they say, prove it. Do it both ways and show me the same answer. Is anybody feeling that way? Or are you accepting that this is true? Your doubt? You see, there's doubt. Okay, so what I'll do is I will do this question twice, and I will use two different turning points, and I'll show you get the same answer. Okay, so line down the middle. T plus S equals 0.981. So I'll do this one way and then another way. Right, in this one, I'm going to I'll make this the turning point. Okay, so if this is the turning point, what is this force? It's clockwise or anti-clockwise? Anti, this one, clock, and this one, anti. So this plus this should equal this one here. Yeah? Right, so what's the first one? That would be 0.25 T plus 0.9 S equals 0.5 times 0.981. So that's 0.25 T plus 0.9S equals 0.4905. One equation, another equation. Now, did you learn how to solve this with, who's your math teacher, Ivan or Joan or Ivan? Did you learn these in math class, how to solve these problems? Yeah, what are these problems called? Simultaneous, yeah? I will be lazy and solve it on the calculator, because I'm lazy and I'm tired. Mode 51. No, it's great, isn't it? It's great being lazy. Okay. T is this. and S is this. Now, for the doubters and the haters, let's see it the other way. We get the same answer. If I can choose any turning point, a convenient turning point to use would be this one. Because is this clockwise or anti-clockwise? It's not, it's nothing, yeah. This one, clockwise, and this one, anti-clockwise. So I can say this, what's that now? 0.25 times 0.981 should equal this one. What's that? 65? Is that 65? 65 S. Now you realise, oh, that's really nice, because I can just say now S equals this. Let's see if I get the same answer. Mode 1. Ready? Hold on to your table now. We should get 0.377. Dun 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 dun. We do. It's the same answer. So S equals 0.377 newtons and T equals 0.604 newtons. So the lesson here is, when it's not rotating, you are free to choose the location of the turning point. You'll get the same answer, which is very, very, very useful, because you saw how nice it was to use this as the turning point, because it cancels the T, leaving me only S. Very useful trick. This is a very useful trick. You should remember this for the exam. It saves a lot of time. Okay? So can you write this down? And I would like you to write both ways. Nearly have this.
Why can we use any turning point for the previous example?
The seesaw example? Oh, still don't believe me. Still doubters. Why can we use any turning point? Yeah, like your question is, why shouldn't I use the actual physical pivot? Is it? Like, you want to know why can I use any point? It's a little bit weird, but the best example I can kind of give you is, can I scroll to the left? Yeah. I don't know if you'll be happy with this, but let's say I have some object here and there's a force this way, and I don't know, maybe there's a force this way. Now we can see that they cancel, right? They will cancel. Even if I put my centre here and draw this as X and this is Y, you know, it doesn't, my point I'm trying to make is it doesn't matter where I put the origin. Like if I draw this here and this here and make this the centre, the mass doesn't care where I call the centre. Kind of the same thing with the seesaw. It doesn't care that I call this the centre. Like it doesn't know that I say this is X and this is Y, and I'm looking at how things rotate around this point. I know that's not a great answer, and if I was you, I'd be unhappy with that answer, but I don't know, does that help or not help?
So for the seesaw, we can also use any.
Yeah, we can, believe it or not. For the seesaw, you could get this. You will get the same answer even if you use the boy as the turning point. Now, the reason we're allowed to do this is because it's not turning. So, because it's not turning, we are free to put the turning point anywhere because it's not turning around anything. It's kind of weird.
Oh, for the seesaw, it's not turning.
It's not turning. So because it's not turning, we can put the turning point anywhere because it's not turning around anything.
I thought one is heavier than the other one.
True. And it would turn, except the father moves the pivot so that it does not turn. In the beginning, remember, it was like this, and of course it turns, so the father moves it so it does not turn, and we worked this out to be 15 centimeters. Yeah.
But if you say that the boy was the turning point, then it would say from the boy to the right.
Yeah, correct, yeah. And in fact you realise, oh, maybe that would have been maybe an easier way to do it. Or, in fact, you might even say perhaps the easiest one to use is the boy, because then it's very easy to see all the distances. Like that's an X, and then the girl is a 5 away because she's at the other end of the seesaw, you know. So, for these ones, maybe you want to put the turning point at the beginning, but you realise there's a problem if you do that. If you put the turning point here, then you will now have to consider the or as a anti-clockwise, because the or is turning this way around. So then maybe you realise, oh, maybe I don't want to do that, maybe I do want to keep it here then. It doesn't really matter because you'll get the same answer, just like how I got the same answer here, using these two turning points. Yeah?
So is the situation like where it's turning, can we still make it not turning, like move the pivot and...
In the exam, it's always not turning. So the question will always be, you know, find the blank if the system is in equilibrium. Yeah. I have never seen an example where it is turning. It's always in equilibrium. Of all the topics in semester 1, there are 2 lessons that students find most difficult. The first one is projectiles, which I understand why. And the second lesson is this topic, which I don't understand why. Because the projectiles seemed a lot harder than this. But I think maybe it's just difficult to picture, to understand. Yeah. Let's continue. This is a silly example. I need to change this. It's so stupid. Yeah. No, I'll change this. I don't want to do this. I do it every year and I don't like it. I need to make a better one. Okay. For the exam, this type of question here with the meter stick, this is a very common sort of quick section A question in the exam. Because you realise it took me longer to do because I did it twice. You know, if you didn't do it this way and only did it this way, it's actually quite short because you quickly get the S, and then you can get the T from just using this. So this actually is quite short. So what I want you to do is I want you to try these for a few minutes in your workbook. Oh, you have the book, don't you? Yeah. How many questions did I give you on that? 3, 4? Oh, nice. Okay.